8.5, our first of 3 volumes. This one is volumes by cross sections. So this is taking, well, what we'll get into is a flat 2-dimensional space on the XY axis, right? And putting cross sections on that flat space that then form a 3D shape and being able to find volume of that, okay? Now, before we do that, we're going to review some basic area to get us started. And let's see, if we read the beginning here, I think it's probably what I just said, yeah. We're going to use calculus to find volumes of 3-dimensional shapes where the cross sections, it's like what we put on our graph, are geometric shapes like squares, triangles, semicircles, rectangles, you know, just basic 2D shapes. Finding the formula for the area of the cross section can be the tricky part. Once you figure that out, it's just integrating like we've been doing. In general, if the cross sections are perpendicular to the x-axis, you solve the equations for y, so you work in terms of x. If the cross sections are perpendicular to the y-axis, then you solve the equations for x, and we work in terms of y. So kind of like if it was upper minus lower, we worked in terms of x, okay? Same type, you know, if it was right minus left, we worked in terms of y. Same type thing. Sometimes we'll work in x, sometimes we'll work in y. Now, basic area formulas. Okay, so just some review. How do you find area of a square with side length b? Because that's what they have in the picture there. B times b or b squared. Okay? How do you find the area of this rectangle with the height equaling 1/2 the base? Got why they did that?
1/2 b times b.
Okay. Because basically they're saying what? This side is 1/2 b, right? So 1/2 b times 1/2 b times b is going to be what? 1/2 b squared. So basic concept, length times width, right? How do you find area of a semicircle with, I'm just going to generalize side length b.
Half pi b over 2 squared.
Yes.
Because what is b technically? I didn't throw in the vocabulary. It's the diameter, right? I didn't throw in the vocabulary because I didn't want to. But we really need to know the radius. And the radius is going to be 1/2 b or b over 2, whichever way you want to write it. Okay, so when we do this area, and I'll clean it up here in a moment, semicircle, you guys said 1/2. You said pi, and then radius squared, so b over 2 quantity squared. Now, if we clean this up, what is 1/2 times pi? That would be better written as what? Pi over 2. What is b over 2 quantity squared? B squared over 4. What's pi over 2 times b squared over 4?
B squared pi
b.
Right?
Yeah, and I mean, we kind of what? Side note here, what I said we were at pi over 2 and b squared over 4, right? And really what they'll generally tend to do is they'll put the coefficients out front. So what if I say pi over 8 times b squared? Because that's your constant out front, is your pi over 8 b squared. Okay, it all depends on what they give you, right?
Yeah.
Okay, moving on. Isosceles right triangle with base as the leg. So what you're seeing there, isosceles right triangle with base as the leg.
squared.
1/2 b squared. Because if they're saying isosceles, that means there's two sides the same, right? And so this is B and B. Area is 1/2 base times height. So 1/2 base squared. Now, change that up. What if they say isosceles right triangle with the hypotenuse as the base?
Then it's okay.
B squared over 4.
How'd you get B squared over 4?
Because if you do B times B, it makes a square in that triangle. That square line by that triangle before.
Okay.
Get the shape.
I see what you're saying, yeah. And it's the right answer. I just wondered how you know, because not at all how I'm gonna go about that. But I see where you're at. Okay. I guess when they put a triangle like this, and you know the base, generally we think 1/2 base times height, right? But what has to be true of the height? It has to meet it at a right angle, yes? And so, since that's, you know, an isosceles right triangle, your height is that middle piece. Now, I like what Aiden said. The way I'm taking this is that if that's an isosceles right triangle, what are those other two angles? What would these angles be? If that's 90, then these two have to each be...
No, that's not right. 45.
I was looking for 45. I was waiting for someone to save you there. Okay. And so and I guess technically, what do we have up here? This is a 45 on each side of that, right? So what do we know about 45, 45, 90 triangles?
I don't know. Geometry was a long time ago.
Oh, we did this in Trig, though. We did this a little over a year ago. It's on my sideboard over there right now for my current pre-calc kids.
Oh,
1, 2 is like
Where
they equal 1. It's like
the legs of a 45, 45, 90 are the same, right? So if you think, maybe I'm making this too difficult, I'm beginning to wonder, but if you think of this right here, that is a 45, 45, 90, yes? And what do we know about this piece down here? If this whole side is B, then this side is 1/2 B. Sorry, can you see that yellow at all? You know, yellow was a good idea to highlight it, just not a good idea to continue. There, better? And then what else do we know then? The height of that triangle is 1/2 B. What I'm trying to get you guys to is we need area for this whole triangle. And what do we normally say? 1/2 times the base of the triangle, which the full base is B, times what's the height of this triangle the way I did that? 1/2 B. Okay, now, when you multiply 1/2 times 1/2 times B, you do end up with 1/4 B squared. Okay? Or, Aiden saw 4 triangles go together to make a big square. And so it's 1/4 of a big square, so a 4th B squared. I'm not going to argue that one either. Okay? Just not the way my train of thought works, so. Okay, guys. Being able to figure out these areas of these triangles is important. Now, what about equilateral triangle? Huh? All angles are the same, which means all angles are what? 60? 60. And this guy up here is 60, or it's split into two 30s. When I draw in the height, does that make sense? So 30, 60, 90. Yeah, geometry was a long time ago. We also talked about last year in trig and pre-calc. How we quickly forget, all right? So if we just focus on
The size is the size of both feet.
officially, what is this bottom side of my pink triangle down here? It's officially 1/2 B, yes? We have to take that into consideration when we talk about a 30, 60, 90. So, and that is what's opposite the 30. So that's my base side. The hypotenuse is 2 times that. Well, 2 times 1/2 B, hey, guess what? Didn't we already, you were just saying that all sides are B, right?
Yep.
What's the height? Well, the height is square root of 3 times the short leg. So what's my short leg here? My short leg is 1/2 B times square root of 3. And that is square root of 3 over 2 times B. So guys, 30, 60, 90. That short, the 30, we always say 1. Think of that as your base length. The hypotenuse, we said 2 because it was 2 times the length of the short leg. The side opposite 60, what I call the long leg, we said square root of 3 because it is square root of 3 times the short leg. Okay? I know, that probably is taking you way back to geometry, but when we put this all together, 1/2 times the base times the height of a triangle, which is square root of 3 over 2 times B. Put this all together and we end up with square root of 3 over 4B squared. I feel like it was in my previous calc notes when I talk out of the Saxon book. I don't remember, but that is area of an equilateral triangle with side length B. There was this point where I know I read that that's just a good formula to know how to do the area of an equilateral triangle. We know the area of a triangle, right? 1/2 base times height, but area of an equilateral triangle isn't a bad thing to know. Now, I'm not saying you're necessarily going to remember that, but if you have a spot in your memory you want to commit that to, it's helpful to know. I will say it's been a moment since I used it, so I'd kind of forgotten exactly. I knew kind of what it was, but I'd kind of forgotten it too. So, okay, guys, as we move on to talking about cross sections on the next page, notice 4 cross sections of area A taken perpendicular to an axis. So when we talk about cross sections perpendicular to the x-axis, so here's your x-axis, right? That means when we're putting in these cross sections, and I'm going to show you what I mean by that here in a moment, if they're perpendicular to x-axis, notice you're working in terms of x. In other words, your equation is y equals, and it's in terms of x. Does that make sense? However, if the cross sections are perpendicular to the y-axis, so now if we're talking horizontal cross sections, now you're going to be working in terms of y's and everything, so it's x equals, and your equation is in terms of y. Okay? Okay, guys. Now, let's look at example 1. When I do this lesson, I should invite Mr. Huntley in sometime to draw the first picture, because let me tell you, that would make things a load easier on me. Now, I was kind of searching, trying to find some images that might help give you an idea here in a little bit, but So example 1, they give us this base figure, right? What do we have? Part of a graph, which we'll talk about in a moment. It asks us to find the volume of the solid whose base is bounded by the function y equals square root of x equals 4, and the x-axis. So we specifically, you can't have just like an unlimited, you have to be on a certain boundary here. Each cross section is a square taken perpendicular to the x-axis. Now, this is where my artistic ability is seriously lacking, okay? Sorry. So you guys see y equals square root of x, yes?
Yeah.
That's that. It technically keeps going, but they're telling us we're going to cut it off at the line x equals 4, and then the x-axis is your bottom boundary. Now, what they're saying is we are going to put squares, an infinite amount of squares, technically. They're going to create a solid. So the idea is when it says the square is perpendicular to the x-axis, my base of my square goes across here. Now, that's just a random spot that I picked, okay? Don't have any reason for pick that. And the idea is the square is standing up. Now, how do I get this square to show standing up? And that's where I can't do, that's a little bit. Okay, so you've got that square standing up. What's going to be over here then? There's going to be another square standing up. And then you've got square beside square beside square beside square. Okay? So an infinite amount of squares. It's not, and the idea of the infinite amount of squares is they get infinitely small, and together they form a solid object. I see a lot of skepticism in the looks of, I'm trying to visualize this, right? Okay? And so I don't think I'm going to leave this on here, but the idea, so yeah, it gets, I just usually draw one cross section, but the idea is lots of squares together. Okay? Now, I did not get this brought up on the computer where I could bring it up on the screen. Let me see. Okay. I'm going to show you guys some of these, and I'm going to say just you can move to be behind me, because I did not get this brought up on the screen like, I should have. But like, oh shoot, it doesn't bring it. So like right here, you will sometimes see teachers, I've never done this, but I wish I could make it bigger. Nope, that's not what I want to do. Sorry guys.
Let's have a project day.
But, I mean, so the idea here is, like, I think this one is squares. So you have a small square right here. As the base of the square gets bigger, the height of the square is going to get bigger, right? And so the idea is it forms this three-dimensional object here. And it would be solid. It wouldn't just be in pieces. Am I not on the page I thought I was? Okay. So here's one where, if you're looking at the base, it's on the ground. These are rectangular cross sections. This blue here, this whole shape is what, if you did rectangle, 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 all these rectangles, that they would form that figure. Here's one with triangles. Okay, you notice there on the ground, there's a semicircle, right? So if you look at the graph of a semicircle, and then each cross section being a triangle, you've got triangles standing up next to each other. Does that help me a little bit or no?
Yeah.
Okay, those are, so each of these, and I'm not saying we necessarily have to visualize what they're going to look like, because easier said than done. That looks interesting. Or, no, that's taking us more into the next lesson. I don't want that. I have some good rotation ones. I didn't have any good cross-section ones. Here's one where you can see, looks like it's kind of a parabola line crossing. Square, each of these squares, right? So there's all your squares standing up. Here's the idea of what it looks like. So there's 9 pieces of square. here's 150 together, how it becomes more of that solid object. Okay? So that's how we're finding volumes of these 3D pieces here. Okay? And yes, this is a project we could do. This would be like if we had a bunch of time after the AP exam, this would be a project to think about. But usually after the AP exam, you guys leave on senior trip, so I don't have to worry, if I needed something to do with our time there. Go look back if you're there. Maybe I did have one that would build the cross sections, but I don't think so. Now, okay, guys, as we look at this shape here, okay, we are looking at. Gosh, that scared me for a moment. Totally lost track of how much time we've had in class today. I was like, what? Okay, so the idea, if you remember from what I mentioned on the first page, is in order to find the volume, we're going to integrate the area. Because each of those little rectangles is one little piece, or squares in this case, okay? The area, or the integral, is going to find the accumulation of all of those. So if we find the area of one square, the integral is the accumulation. So it's going to be the accumulation of all the squares from 0 to 4. Okay? Now, we need to talk about area of a square here. We just talked on the other page. What do you know about area of a square? B squared if the base is, if one side is B, yes? Okay. We can't use B. We have to have this in terms of our equation. Okay? So we're looking at the base of the square goes from the x-axis up to that curve. Okay? So I want to know the base of that square, that distance there. Well, is it always going to be 2 though? I mean, mine's a little bit more than 2 where I happen to have it drawn, but is it always going to be the same? No, because a square over here is going to have a much smaller base, right? Square over here is going to have a much bigger base. We need something that works in terms for all of them. This curve is square root of x, right? So what's the distance from this curve down to the x-axis? It is square root of x. Okay? Because that curve is always going to be the distance from the curve to the x-axis. That's going to be square root of x. So square root of x is my b value, yes? Does that make sense? And I'm not always going to write this out. Beginning steps here. So, I was looking to see how I have this. Okay. I guess I kind of put it over here on each of these is what I forgot. So area is base squared. Now, officially what you'll see me do, the base of this square is really a distance of y, yes? Here, I've got another, I need to throw this in because it'll help with later understanding. This height of the square from here to here is a distance of y, correct? So we could also say y squared, but what was y in terms of the equation? Square root of x. So do you see where I'm going with that? So my area is going to be the square root of x squared. Which, yes, you can clean up. Okay. And you can eventually think x if you want. Okay. So, all we have to do is integrate this, guys. I say all we have to do. But it is, I mean, truly. We're going to do the area. Or, excuse me, we're not doing area here. We're doing what? Volume. The volume. It's the integral of area. So how do we find the area of this square? We decided it'd be the square root of x squared. We're working in terms of x, so this is dx. Okay, each rectangle is represented with a width of dx.
Can we go ahead and clean that up?
I will, yes. Yeah, you can go ahead and clean up right now if you want. Because we did do it over here, but I just want you to make sure you know where that X randomly comes from. So yes. What are my bounds?
0 to 4.
We're going from 0 to 4 on the x-axis. So yes, we are really doing the integral from 0 to 4 of x dx when you clean that up. And let's integrate. What's the integral of x?
1. No.
Integral, not derivative, right? 1/2 x squared evaluated from 0 to 4. Get a final answer of 8. Because 1/2 times 4 squared is 8. And then 1/2 of 0 squared is 0. Okay, guys. Questions with this cross section of squares? Okay. Now, is it always going to be a square cross section? We wish, right? And that's, I'll be honest, cross sections are not the easiest thing. Okay? Because you have to think about each individual object. Okay? Every problem's a little different. The idea is to find the area of the cross section and integrate it. But finding the area of the cross section within the problem is the catch. Okay? Okay, let's look at number 2. Find the volume of the solid whose region is bounded by the circle x squared plus y squared equals 9 with the cross sections taken perpendicular to the x-axis that are isosceles right triangles with the hypotenuse line on the base of the circle. Okay. We just stepped it up a big notch.
Yeah.
I know. I hate that we step it up this big of a notch, but there's a lot to take in here.
Is it? Can't you just? Oh, there's still squares.
Right triangles with hypotenuse line to the base of the circle.
Oh, it's triangles.
Every problem's different.
That's a base of the circle.
So it's like half of this circle.
Okay.
It's like half of the ball.
Can we do, wait.
Well, so this is our base right here. We're using the whole circle.
Right.
Okay, so this is our base, that x squared plus y squared equals 9, which eventually we'll have to solve. Cross sections taken perpendicular to the x-axis, which means here's perpendicular to the x-axis, right? So that's like one of my bases. And that cross section is isosceles right triangles. So, and this is where, I don't know, do I want to move it? You know, there's another one over here. Whoa. Oof. Just trying to figure out where's the best place to draw my triangle. I can't. Oh my goodness. Why is this so difficult? So my triangle,
Oh.
you got all these triangles standing up, right? It's standing up. How do I draw it standing up?
Oh, so like
Going
this?
out?
Like coming out this way.
That way, okay.
But like,
Coming out of the bin queue.
Got it.
How do I draw that though?
I don't know.
I don't know.
I
Okay.
was thinking.
Like, and that's the idea. Like, yeah, they're standing up. Like those images I showed you.
So it's like a party hat.
Sure.
It's more of a
It's not bad.
like a cone. A cone.
Yeah.
Like a sideways cone.
Not exactly though, because you're going to have a line of the tops of triangles.
Yeah, but
So like
it's like the thing in Australia.
What? Huh?
that,
Wait, the dome, whatever?
Yeah, that.
the place where they have concerts.
Is it though?
I can't visualize what that one looks like to remember.
The one that has like the.
I don't know. It's
I don't.
Yeah. So the idea here is, think these triangles are going up on the sides, right? So you've got triangles piled along. They're going to go up, but they're not going to be, well, kind of, because as they get wider,
They get bigger.
they get wider and wider, and then they get skinnier and skinnier again. But they're going to go up to a ridge at the top. It's not going to go up to a point, because even the triangle right here, even the smallest triangle goes up to a point. They go up to a point. Your points get higher as they get wider, and then they get smaller. If I wanted to take time to search, I bet I could find something, Okay, now, here's the deal. In all honesty, do you have to know what the final picture looks like? No. It's interesting to know, and it's good to think about, but technically we don't have to know it. We have to know the area of that triangle, and we have to integrate it. Okay? Now, with that in mind, okay, we're going from here to here, yes? I'm going to say the distance from the x-axis, so like what I kind of talked about in the last one, the distance from the x-axis to the top of the curve, if I say that is a distance of y, and the distance from the x-axis to the bottom of the curve, that is a distance of y, correct?
Yeah.
Okay, so that means the base of this triangle is how long? 2y. Now, this is perpendicular to the x-axis, which means we need to know what 2y is in terms of x's. Okay? So, now, here's the deal. I'm going to set up our area formula in terms of y, and then we'll translate it to x's based on our equation here. Area of a triangle. 1/2 times the base. What's my base?
2y.
2y. Are you seeing that?
Yeah.
Okay, so that's like we're doing 1/2. There's base. Now, here's the deal. We need the height. Keep in mind, what kind of triangle was this? Isosceles right triangle with the hypotenuse laying on the base of the circle. So here's the hypotenuse. Technically, where's the right angle then? The right angle is up there. Now,
What?
we backtrack to the previous page for a moment.
Yes, sure.
Flip back to where we talked about areas. Isosceles right triangle, hypotenuse laying on the... Let's talk about this guy.
So,
Okay. Now, at this time, though, what was our base?
2y.
It was, well, but this was b, and we said it was 1/4 b squared. So we're going to go over to the other page and say 1/4 2y squared.
So 1/2 y squared. As our no, that's b squared.
Okay, that's going to work out okay. Sorry. I started stressing that it wasn't going to work out the way I needed it to work out. Okay. What does that clean up to be? Did you guys get it?
1/2 y squared.
Yeah. If we do it this way, and I'll show you, 2y quantity squared is going to be
4y.
4y squared.
Oh,
And then 1/4 of 4y squared is
y squared.
y squared. Or, here's the other way to think about it, guys. Draw that triangle. We said this was y and y, right?
Yeah.
This is a isosceles right triangle with the base here, right? Which means this falls back into that 45, 45, 90s. This would probably have been the easier way to go. If this is y and y, that gives the length of 2y all the way across, but all we need to know is this is y. What's this piece up here? If this is a 45, 45, 90, it's also y. Okay? As I said, this is the hard part right now. Okay? So when we talk height, that's going to be y. If you memorize all those area formulas we just did and what they mean, okay, that's the way to go. I took you back there without thinking about that. The other way to go is, okay, think about this. 45, 45, 90. If this is y, then my height has to be y because it's the two sides of a 45 are the same. Now, if you clean this up, 1/2 times 2 times y times y. Y squared. So area is going to be equal to y squared. Now, we're not working in terms of y though, right? We need to know what that is in terms of x. So remember, they didn't give me an equation that was solved for x or y, did they? We have to solve it appropriately. Okay? We're working in terms, since it's perpendicular to the x-axis, we're working in terms of x, so solve this for y. So what? Y squared is 9 minus x squared. Can we?
Yeah.
Do you guys see that?
Yeah.
I mean, you could keep solving and say, okay, yeah, this is y is plus or minus the square root of 9 minus x squared. But here, guys, y squared is 9 minus x squared. What are we going to have to use as our area? Y squared. So can you do that shortcut?
Yes.
Yes, and you should. Okay? So, let's see if we can work on setting this volume up. Okay. We are integrating the area. It was going to be y squared, which in terms of x is what? 9 minus x squared times dx, which represents the width of each little triangle here in this case.
From -3 to 3.
Does that make sense? From -3 to 3. I have an or option if you want it.
2 and then do 0.
Is this a symmetric base?
Yeah.
This is. Okay, this is a symmetric base. Two halves of the circle are definitely the same. So could you instead say, I want to go 0 to 3 and multiply that by 2?
Yeah.
You can. So, or the integral from, whoops, hold on, don't forget the 2. 2 times the integral from 0 to 3 of 9 minus x squared dx. Any calc knowledgeable person is going to be supportive of either or. Okay? Now, either way we do this, we need to integrate, yes? Which one are we doing? You want to go from -3 to 3 or 2 times 0 to 3?
2 times 0.
Okay, so let's do 2 times 0 to 3. Okay, so keep your 2 out front. What's the integral of 9? Minus, what's the integral of x squared?
1/3 x cubed.
Evaluated from 0 to 3. Don't forget your 2 out front. Guess I kind of lost my v equals there, didn't I? But 9 times 3 is 27. A third of 3 cubed. Well, I know 3 cubed to be 27. A third of that is 9. 27 minus 9 is 18. 18 times 2 is 36. So the symmetry thing still applies. Use it when you can. Okay. I feel like she threw a really tough one at us. Not first, but second. So, okay. Ready to keep going?
I guess so.
I guess I'm not giving you a choice, but I made it sound like a question. Sorry. Number 3. Let R be the region bounded by the graphs of x equals y squared. So x equals y squared is that sideways parabola. X equals 9. That's just cutting off the parabola at 9. Find the volume of the solid that has R as its base if every cross section by a plane perpendicular to the x-axis is a semicircle. Okay. Is Tate drawing it in the air?
Yeah.
We are perpendicular to the x-axis, semicircles. So my semicircles, oh my God, why can I not draw a straight line?
This one's like bell shaped.
Yeah.
Okay, and so now these circles are standing up, right? Or these semicircles are standing up. Now we're not going to have that ridge directly on top, are you? I mean, think, this side is a semicircle. As we move to the left, so at the right you have your biggest semicircle. As you move to the left, each semicircle gets smaller, yes? I feel like, did I see that? Oh, nope, I saw it with similar shape, but it was with squares, so not exactly. Okay, guys. So we got semicircle there. Now, what are we talking about with area of a semicircle? If we just talk basic area of a semicircle, what? 1/2 pi r squared, yes? Now, I'm going to talk about this because this is vertical from the distance from the x-axis up is a vertical distance of y, right?
Yeah.
Because that's going along the y-axis. And the distance from the x-axis down is also a distance of y. We'll convert it to x when we're ready. Because I'm perpendicular to the x-axis. So again, what are we working in? We're working in terms of x's. Now, what we need to know is we need to know that radius. How long is the radius of the circle? It's just y, yes? Because it would just be one of these. So your radius of your circle is y. So 1/2 pi y squared. Okay. Go to your equation. X equals y squared. 1/2, officially it's 1/2 pi x, yes? Okay, I mean, at some point, you could also talk about that this is what? Y equals plus or minus the square root of x, yes? And you could put that in as square root of x, y is square root of x, and then when you square it, what do we write back at? We're right back at x, yes? So can you just use the given equation in those nice pieces? Yeah. 1/2 times pi, what am I going to write that as? Put those constants together, pi over 2, so pi over 2x. Is it getting a little bit better?
Yeah.
That one was not bad, right? And it's going to vary. Some of these problems are not bad, some of them are rough. Okay. Volume. What are you setting up?
Integral of,
0 to 9.
yeah.
0 to 9.
0 to 9 because we're starting here, ending here. Of, what am I integrating?
Pi over 2x.
My area, pi over 2x. Dx. Okay. Now, officially, if you want to, that pi over 2 can come out front, yes? Pi over 2 times the integral from 0 to 9 of x dx. What's the integral of x?
1/2 x squared.
1/2 x squared evaluated from 0 to 9. Me personally, I'm going to take that pi over 2 and that 1/2, multiply them together and leave them out front, because do I need to plug into those? So I'm going to say this is pi over 4 times 9 squared minus 0 squared. Do you like my answer?
Yes.
I wrote it as 81 pi over 4. 81 fourths pi, I don't know, however else you want to write it. Okay. Number 4, you guys have flipped and you're looking at number 4, aren't you? They get kind of mean.
We have to draw
I
it.
gotta draw it?
Might be a good thing for
Yeah, it's
tomorrow.
tomorrow.
It's definitely a good thing for tomorrow. I'm definitely agreeing there. But now, here's the good news, though. It's find the volume of the solid whose base is the region bounded by the line. They give you a line, guys. X plus 2y equals 6, x equals 0, y equals 0. So it's not a horrible graph to draw. But, okay, we will pick up at number 4 tomorrow.